Okay, welcome to the next video on basically Unit 20, which is just an HL topic. Today we're going to be discussing the exact same thing as last time, which was the factors affecting the rate of a nucleophilic substitution reaction. So we're looking at the factors affecting this. So we've already covered the first factor, which was the identity of the halogen. The second one, which was the identity of the alkane, whether it was primary, secondary, or tertiary. And the third, what we're going to talk about today, is we're going to talk about the choice of the solvent. Choice of the solvent. So this is, what we're going to need to memorize in this unit. We're going to need to memorize what's the choice of solvent for primary and secondary. And then basically we use this choice. If you've ever got a secondary alkane, we use the choice of solvent either for tertiary or primary in order to make this secondary react either in an Sn1 mechanism or react as an Sn2 mechanism. So we're gonna see that how our choice of solvent can affect this. So I'm gonna erase these. We'll leave them there for now. Okay, so basically I'm just gonna make a quick T-chart and then we're gonna analyze why. So we've got Sn2, and we're just going to be talking about the solvents here, versus Sn1. So Sn2 versus Sn1. Sn2, what we want is we want a polar solvent, and we want it to be aprotic. And Sn1, we want a polar solvent, and we want it to be protic. So basically, aprotic means, let me kind of change the color, will mean no hydrogen bonding. So we don't have that H bonded to F, we don't have that H bonded to N, we don't have that H bonded to O. We've got no hydrogen bond. We've had polar, but we don't have any hydrogen bonding. And protic means polar, so we have hydrogen bonding. And as we know from our intermolecular forces, right, we had the London forces were weaker than the dipole, which were weaker than the hydrogen bonding. So it's weaker. So as you remember, right, these, I might spell this wrong, were called van der Waals forces, and hydrogen bonding was an additional one, and all of this is considered, right? All of this we put into the under the name intermolecular forces. And that's what we're going to be studying basically in this, is just basically what intermolecular forces can we have, make this reaction happen faster, and what intermolecular forces can make it happen slower. So we're just going to talk about how these intermolecular forces affect the rate of an Sn1 and an Sn2 reaction. Okay, so now I'm going to erase this top part because I need a bit more space, and then we're going to keep going. There we go. There we go. So basically, for Sn2 mechanism, let's talk about the Sn2 first. So first we'll talk about Sn2 mechanism. So we wanted it to be polar, but we don't want it to be a protic solvent. So why that is, right? So we've got let's see an example I could use. CCl, H, H, H. So now we've just got a chloromethane. And we've got this hydroxide group that really wants to come in and attack it. Why we want a polar solvent, hopefully this makes a little bit of sense, is right, this here is delta negative electronegativity, and this one's delta positive. So the charge moves towards the chlorine. So it's a polar molecule, so we need a polar solvent. It's the same thing for the Sn1s. It's a polar molecule, right? We've got a haloalkane, which is polar. So now we've got a polar molecule, so we need a polar solvent. That's that like dissolves like rule, right? That's why we can't dissolve oil in water. But aprotic, why we want an aprotic solvent is that we don't want, let me change the color. I'll say, we don't want to solvate the nucleophile. So we don't want this nucleophile to get comfortable, right? It's a negative charge. It's sitting there. It's negatively charged. And we don't want it in a comfortable state. We want it to force it to bond. So the more comfortable we make it, the less it's going to want to bond, right? If we had hydrogen bonding here, we've already got hydrogen bonding here, but then we'd have a bunch of different positive charges stabilizing that. So the more positive charges we have stabilizing that, the more stable the hydroxide is, and the less it's going to want to go and give away its electrons. It's already happy, right? It's surrounded by pillows. What's its point of leaving and getting less comfortable? We want to make it uncomfortable. So by using a polar solvent, what we can do is, right, we've got, let's see an example of a polar solvent we could use. We can use a polar solvent like this. We've got propanone here. So, right, we've got, it's trigonal planar. This has a net positive charge, and this has the delta negative charge. It's not a carbocation. I shouldn't have drawn it like that. It's a delta positive charge and delta negative charge. So it can't really solvate that OH molecule that well, right? The positive charge to stabilize the negative is on the center. So if we were to draw that out, 3D, we'd have it like this. So the only parts that could even come close to solvating the hydroxide is either the top of the plane, right? If we looked at this on a plane, it would look like this. A double bond. So the only places, right, that has the delta positive are the top and the bottom of this carbon. And if we start surrounding the hydroxide with these, you can't surround them that much. This is a huge, rather large molecule, and the hydroxide is pretty small. So we cannot solvate it with that many positive charges, just because the positive charge is kind of hidden on the inside. So we don't want to solvate the nucleophile. That's basically the rule for Sn2. We want it to be polar, aprotic, and aprotic because we do not want to solvate the nucleophile. Examples of this are what I drew, examples of polar aprotic solvents. If you imagine what that means, it must be polar, but it must not have any oxygen and hydrogens bonded. Oxygen, hydrogen, no oxygen, no nitrogen, hydrogen, no fluorine, nitrogen, hydrogen. So here we had an example will be propanone, right? One means ketone, and propane means C3, so 3 carbons in a chain. And our second example is going to be ethyl ethanoate. So how to draw that? You draw the ethanoate first, meth, F, single bonded to O, single bonded, your double bond to O, single bond to O. And then the ethyl, C, C. And this is H2, this is H3, this is H3, and this is no H's. So ethyl ethanoate, right? We see no hydrogens bonded at all to the oxygens. It's polar because it's asymmetrical, but there's no hydrogen bonding, so it's not a protic solvent. It's an aprotic solvent. Okay, so that's Sn2. That's why we want to use an aprotic solvent, because we don't want to solvate it. Okay. So the second one, we want it to be uncomfortable. The second one, just let me erase all this Sn2 mechanism stuff, and let's get back to the Sn1s. Okay, so let's go Sn1 mechanism. So we said polar and we want it to be protic. So let's draw another example, right? We need a tertiary, because tertiary is guaranteed one or the other. CH3, CH3, CH3. Let's do a chlorine here again. And let's have it reacting with the hydroxide. So now we want the opposite situation, right? I'm going to take away this hydroxide for now. We want the opposite situation to happen now, right? We've got this chlorine. Let's draw the next step in the reaction. So we've got this chlorine, and it takes the electrons. It's the leaving group. So it takes, through heterolytic fission, it takes both the pairs of electrons and leaves the carbocation. So we've got carbon, CH3, CH3, and CH3. And now it's got that positive charge on it. It's the carbocation plus Cl minus. So why we want a protic solvent, right? It makes sense why we want a polar solvent. This molecule is polar. Polar dissolves polar. So hopefully the polar solvent makes sense. Why we want a protic solvent now is that we want to make this leaving group comfortable. Like, right, we said with the aprotic solvent, we do not want to make the nucleophile comfortable, but the thing is we want to make the leaving group comfortable. So we make it protic in this case, because then, right, if we had water around here, we'd have a bunch of negative charges solvating this chlorine. Plus, plus, negative. We have another one here, H plus, H, oxygen. So we can solvate it with a lot of charges surrounding it, top, bottom, all around the circle. So, if you imagine, it's like jumping into, right, here he's bonded, he's got some electrons and he's happy, but then he jumps into basically a pillow, jumps into a bunch of feathers that just stabilize his charge. So he feels more stable out here than he does actually bonded, because now he's comfortably solvated. So then he can leave, right? He can move further away and not be as attracted to this positive charge. He's got a negative charge. He wants to give that back. He wants to give it back and neutralize, but all these positive charges are stabilizing that negative charge, so his need to give it back is less. So he's very well solvated. And also, right, so also, now that he's solvated, we've got the hydroxide that could come in here. The hydroxide, though, this is the trade-off, right, is that the hydroxide is also solvated in the water. So it's also solvated in the water. So we've also made it comfortable and reduced its reactivity. But the thing is, right, like we said, this hydroxide bond to the carbon, sorry, that's drawn wrong, OH, bonded to the carbon, is stronger than the chlorine bond to the carbon. So the thing is, although he's comfortably solvated still, he's got a stronger bond with the carbon when he forms it. So he's happy to form it and reduce the overall energy of the system. So, right, this is again just those enthalpy calculations. We're the enthalpy of solvation, the energy it gains through being dissolved, in this case, is going to be less than the energy of the bond. So whereas with the chlorine, it's going to be the opposite. The energy of solvation is going to be greater. The energy loss based on solvation is going to be greater than the energy gained by forming the bond, by the energy released by forming the bond. So it's just, it's all thermodynamics at this point. So he's solvated, but he's got those, those lone pairs he still has. And like I said, him forming that bond will make the system more stable than if chlorine was bonded there. So you've got an overall, exothermic reaction, overall spontaneous reaction. If you remember your delta G, your Gibbs free energy calculations. So yeah, that's basically why we want the protic solvent is. The way I like to think about it is we want to solvate that leaving group. It doesn't matter if we solvate him, because that's not the rate determining step, right? The rate, which is what you have to keep in mind, is K times the nucleophile. If we can make this nucleophile very, very happy leaving, he's going to leave more and the rate is going to increase. We can speed up and make this process more efficient. Yeah, and basically that's it. So I'm going to erase this down here and I'm going to give you some examples of a polar protic solvent. Okay, so a polar protic solvent, our examples are going to be methanol, which hopefully you remember, meth means one carbon, 3 hydrogens, and a hydroxide group. So right, this is what I said. We've got the hydrogen bonding. The second one we're going to have water, H2O, right? OH, delta negative, delta positive. We've got hydrogen bonding here. We've got some hydrogen bonding in here. And those are basically the 2 that you need to know. So let's do the last one. The last one we're going to talk about is the secondary. Let's go up here. Let's just erase this. Sn1/2, because we're going to be dealing with secondary now. So this secondary, right? You can take a second. We said secondary carbons can undergo either Sn1 or Sn2 nucleophilic substitution reactions. But based on what we previously covered just a second ago, right? We said that Sn1 prefers polar protic solvents, and Sn2 prefers polar aprotic solvents. So we can use this to push this towards Sn1 or Sn2, right? Let's draw a secondary. So we've drawn a secondary now, a secondary carbon. And if we wanted him to undergo Sn1, right, then like I said, we need to make the environment comfortable for this leaving group. So we use polar protic solvents. We want, this carbocation, CH3H, with a positive charge. We want to solvate this. We want him to be surrounded by hydrogen bonding so that he's stable. So we can force it to go through the Sn1 reaction mechanism, right? We still have that inductive effect where all the neighboring carbons are going to donate some electronegativity, and that can stabilize the carbocation. So that's basically how we can force it to go towards an Sn1 mechanism. And we make that nucleophile group, we make it more comfortable too. So it stabilizes the nucleophile, and then the nucleophile can come in comfortably, bond, and reduce the energy of the system. In contrast to that, right? We can undergo a different one. We can take this one and we could use an aprotic solvent. So the aprotic solvent, right, doesn't solvate this leaving group that well. So it makes him want to stay attached to that carbon. His energy of solvation is not going to release enough energy that it's worth breaking this bond for. It just can't happen. So then when you've got this mechanism, right, we've got an unhappy place for the chlorine to go. He's not happy going there. We've also got the hydroxide living in a very unhappy environment. So what he's going to do, right, now it just depends on bond strength. So if this carbon hydroxide bond is going to form a stronger bond than the carbon chlorine bond, it's going to happen. And that's what we see happen, right? It's going to come in from the back side. If we imagine we've got, I'll draw that with chlorine to the top. Chlorine, CH3 coming out, CH3 coming out, and going back in the center is your H. We're going to have that hydroxide do the same thing. Come in the back side, donate his electrons. These electrons are going to pop up to the chlorine, and the chlorine is going to leave. Once it's formed the new bond, it doesn't need the old bond anymore. So remember, we're going to go through that reactive intermediate that I covered in the last video, or in this video series for this chapter. So if you haven't watched them, I recommend you watch over them. And we're going to cover that reactive intermediate. It's going to form that reactive intermediate again, and it's going to react. So this is how we can force a secondary carbon to undergo either Sn1 or Sn2 addition. And why we'd want to do that, right? We end up with a similar product. But the thing is that with the Sn1, right, we don't have no inversion. So we have no inversion. With Sn2, we had the inversion. So when the stereochemistry matters, it depends. Do you want to flip it, or do you not want to flip it? And you can make the decision by choosing your solvents properly. So I hope this video was useful. I'll see you again in the next one.